Hello and welcome to today's webinar by LS Instruments. In today's event, we will be talking about protein solution microviscometry with the NanoLab 3D. My name is Colin Bretz and I'm the marketing and sales manager at LS Instruments. I joined the company 3 years ago in 2017 after completing a PhD in colloidal self-assembly from the University Paris 6 and the University of Pennsylvania. And I would like to introduce our featured speaker for today, Professor Peter Schurtenberger from the Division of Physical Chemistry at Lund University. Peter is also the former director of the Lund Institute of Advanced Neutron and X-ray Science and the former director of the Adolf Merkle Institute of Science in Freiburg, Switzerland. He is also a member of the Royal Swedish Academy of Sciences and an honorary member of the European Colloid and Interface Society. Before we begin, I would like to remind you that this is an interactive event and that your questions are welcome through the chat located on the lower right side of this webinar window. In the first part of the event, Peter will give us an introduction to DLS microviscometry and to the 3D technology. And I will then conduct a demo on the NanoLab 3D using a BSA protein solution. And please stay with us at the end of this event as we host a question and answer session from the question you would have asked us in the chat. Before we begin, I would like to just say a few words about our company. So LS Instrument was founded 10 years ago from a spin-off of the University of Freiburg in Switzerland, and our specialty is light scattering technologies, mainly static light scattering, dynamic light scattering, and diffusing wave spectroscopy. And our goal is to provide the most advanced and trusted solutions to our customer to solve their analytical challenges. Our customers are academic and industrial scientists in more than 30 countries, and our portfolio consists of mainly 3 instruments. The LS spectrometer, which is a goniometer-based instrument for DLS and SLS. So this is an instrument that can be configured with different options. The 3D technology, a sample goniometer for non-ergodic sample characterization, and also a depolarized DLS unit. We also offer the NanoLab 3D, which is our focus for today, a fixed angle particle sizer that can perform measurements while suppressing multiple light scattering. Very important to characterize concentrated samples. It also features our newly developed Coran algorithm for accurate DLS analysis. And if you've been with us last month, you also know about the DWS ReoLab, which conducts fast, reliable, and contact-free viscoelasticity measurements using the DWS technology. As we start now, I would like to hand the floor to Peter, who will be giving an introduction to DLS microviscometry. Peter, the speech is yours.
Thank you, Colin, and hello everybody. It's a great pleasure for me to give you a short introduction to protein microviscometry using dynamic light scattering. Now, protein solution viscosity is actually a key quantity. Knowing protein solution viscosity is essential, for example, for current attempts to formulate high concentration protein solutions for drug applications, because there, at these high concentrations, injectability is always a concern, and that requires that the protein solution viscosity is below a certain limit. It also is a key property if you want to monitor the stability of protein solutions. It allows us to some extent to say something about the expected shelf life of such a sample. And in general, we know that solution viscosity for proteins may vary enormously between different proteins. This is shown here with the example of data from 2 monoclonal antibodies and from 2 globular proteins. One is a lens protein, the so-called alpha-crystalline, and the other one lysozyme. And we see that in all cases, the relative viscosity, that means the ratio between the solution zero shear viscosity and the viscosity of the solvent, it increases dramatically with concentration, but this concentration dependence looks very, very different for the 4 different proteins. Why is that? Because protein viscosity or solution viscosity actually strongly depends on protein interactions, and in particular on the ability or the tendency of proteins to aggregate to form clusters. And therefore, measuring and understanding protein solution viscosity also tells us a great deal about protein interactions and the effects, for example, of certain excipients on this solution property. Now, how do we do protein viscosity measurements? And why should we actually use microviscometry? Well, measuring protein solution viscosity using classical tools is actually not such a simple task. And that has largely to do with the fact that proteins have a tendency to go to interfaces. For example, to a liquid air interface and there form viscoelastic layers. Now, such interfaces also exist in the tools of classical mechanical rheometers. And so if we then try to measure protein solution viscosity at different concentrations, we actually might start to see big surprises. This is shown here with data from lysozyme at 3 different concentrations, 1 very low and 2 rather high concentrations, and also the buffer viscosity as a function of shear rate. And we see that the viscosity, the shear rate dependence of the viscosity of the lowest concentration is actually looking odd. It almost looks like it's a viscoelastic solid. You see a very strong shear dependence or shear rate dependence of the data. That is actually because here what we measure is no longer the solution viscosity, but we primarily see the effect from this viscoelastic surface layer. And only once we go to very high protein concentrations, the bulk viscosity then starts to dominate what we measure in this mechanical rheometer. Moreover, these typical rheometer tools for classical rheometry use rather large sample volumes. And that is, of course, almost prohibitive when we look at the precious proteins that we may make in protein engineering experiments and in early stages of drug developments. And so we need a way to actually do experiments that require much less volume and that are also independent of these artifacts, in particular at lower concentrations. And this is where microviscometry comes into play. Important, of course, is that microviscometry experiments actually provide us with the same information as the classical rheology does. That this is the case, if properly done, you see in this comparison here of microrheology and classical rheology experiments from 2 globular proteins, from lysozyme and alpha-crystalline. You see both techniques provide essentially the same data. What is also obvious from this comparison is that the microviscometry data actually carries much less noise, in particular at low volume fractions or low concentrations. And what is moreover noteworthy here is that for the microviscometry experiments we need about 1/100th of the sample volume as we would need in the classical mechanical rheometry. Now, how do we perform such a microviscometry experiment? Well, the basis is a simple dynamic light scattering experiment or DLS experiment. What you see here is a cartoon of a dispersion of particles that undergo typical Brownian motion. And the diffusion of these particles then causes the relative positions of the particles to constantly vary, and this in return then causes strong temporal fluctuations of the scattered intensity that can then be measured with a photon detector. So how does that help us then to do a microviscometry experiment? Well, suppose that the sample container now not only contains colloids, large particles, and a solvent, but it actually contains a protein solution as the background medium. The particles will still, if we do the experiment properly, scatter much, much more than the proteins. And this means that these fluctuations in the intensity that we then observe basically come from the motion of the tracer particles only. With these intensity fluctuations, we can then determine the so-called intensity autocorrelation function. And we know that this intensity autocorrelation function for ideal particle suspensions where the particles don't really interact with each other directly give us the diffusion coefficient of the particles. Now, the diffusion coefficient of particles is, of course, directly related to the size of the particles by the so-called Stokes-Einstein relationship, which you see here. Now, suppose we know the radius of the particles. We measure the diffusion coefficient directly, and this means we now have the viscosity. If this experiment is not done with particles in a pure solvent, but particle in a protein solution, this viscosity then is the protein solution viscosity. And so this means by doing a simple DLS experiment of particles embedded in a protein solution, we have a completely non-perturbing way to study the solution viscosity of the protein without having to impose any mechanical strain on the sample. It's entirely a bulk solution measurement, so we are also not at all suffering from possible artifacts due to any tendency of the proteins to go to a liquid air or a liquid solid interface. And what we measure is the ideal zero shear viscosity. Now, unfortunately, life isn't so simple often. And so there are actually a number of possible pitfalls. One of them in particular, if we have added too few particles. This means in our measured intensity autocorrelation function, there will be both a contribution from the protein diffusion coefficient as well as from the particle diffusion coefficient. If we do conduct these experiments as a simple black box experiment, we won't even notice this. If we look at the correlation function, we see that there are two decays, but actually obtaining accurately the particle diffusion coefficient in this case is not always straightforward and can result in rather large systematic errors. This means we have to add enough particles in order to completely overshadow the contribution from the proteins. And then we are able to actually measure the particle motion only, particle diffusion coefficient only, and thereby also the solution viscosity at different protein concentrations. However, there is another problem there. You see here in this picture in the right upper corner of the right-hand graph that the solution now looks turbid. This is because now we have actually added too much particles. Still, the particle concentration is very low, the particles are non-interacting, we get the proper diffusion coefficient in principle, but the particles scatter so strongly that there is now measurable multiple scattering. And that, of course, will add other errors in our analysis of the data. This can be particularly problematic if we, for example, do these experiments at large scattering angles, as certain spectrometers do. Because often for these experiments we use larger tracer particles to have enough scattering intensity and be able to measure diffusion coefficients properly without suffering also from artifacts from dust or some spurious protein aggregates. Such particles have an angular dependent intensity due to the so-called particle form factor, and that means the scattered intensity at high angles is significantly smaller than at low angles, and so whereas the multiple scattering is basically the same at all angles. And that means then the ratio of multiple to single scattering increases more and more if we go to high angles. And there might actually be a measurable multiple scattering contribution at high angles, even if the solution doesn't really look so turbid. So we need to do something else. We need to be able to suppress this multiple scattering contribution, otherwise we have error-prone measurements. So how can we then perform a reliable DLS microviscometry experiment that both does not suffer from measurable protein contributions, but also not from multiple scattering? Well, this can be done by doing a so-called 3D light scattering experiment, or as a matter of fact, better, a modulated 3D experiment as implemented in the NanoLab 3D of LS Instruments. The principle is shown here. What we now do is we actually perform two dynamic light scattering experiments in exactly the same scattering volume. And we have two detectors that measure then the fluctuating intensities. And the way the geometry is implemented, they also measure the scattered intensity at exactly the same scattering vector. And if we then cross-correlate the fluctuating intensity seen by these two detectors, we then create not an intensity autocorrelation, but what is called a cross-correlation function, which actually has exactly the same information there as the autocorrelation function normally measured in a standard DLS experiment, but now suppresses automatically all contributions from multiple scattering. So one always measures completely multiple scattering free, single scattering intensities, and thereby is then able to do a artifact-free microviscometry experiment. So this means we can now add sufficiently high tracer concentrations to ensure that we do not see or get any artifacts from protein contributions, but still sufficiently low that we are not facing problems due to particle interactions. And we then use the 3D technology in order to suppress multiple scattering, and that gives us then a microviscometry experiment of the highest quality and lowest noise. What can we do with that? Well, one example is shown here, where we actually profit from the fact that when we do these experiments with the NanoLab 3D, we actually not only have a microviscometer, we have a full-fledged spectrometer that is capable of doing static and dynamic light scattering as well as microviscometry measurements. So by doing two experiments, one with, one without tracer particles, and then varying the protein concentration, we can, for example, study, as done here, the concentration dependence of solution properties from a monoclonal antibody. And what you see here are then the corresponding results that show the apparent molecular weight from the static light scattering, the apparent dynamic radius from the dynamic light scattering without the tracer particles, and the relative viscosity then obtained with the tracer particles. And this gives us high-order information on the solution behavior of this antibody. This has then allowed us, in this particular case, to develop a complete model that is capable of describing the self-assembly and its effects on protein solution viscosity as a function of concentration for this particular monoclonal antibody. With that, I'm at the end of my part of the presentation, and I hand over to Colin for the rest of the webinar. And I also look forward to your questions, and at this stage say goodbye.
Thank you very much, Peter, for this introduction to DLS microviscometry. And now that we have a good overview of the technique, I would like to take some time to show you the NanoLab in more details and conduct a demo measurement. On my screen, you can now see the instrument. So this is our fixed angle DLS particle sizer and microviscometer. And as you can see, the interaction with the user is extremely easy with just the on and off button located here, and the sample chamber which slides open here. You can load your samples in our square glass cuvettes with the option of 10 by 10 millimeter, 5 by 5 millimeter, and for fewer amount of sample available, we have a 3 by 3 millimeter cuvette. And for extreme cases where few amount of sample is available, we have this 1 by 1 millimeter cuvette, which holds as little as 4 microliters of sample. The 3 by 3 millimeter cuvette holds 50 microliters of sample. And for the next part of this webinar, I will conduct a demo measurement on a BSA protein solution, which you can see in this cuvette. And since we're doing DLS microviscometry, I need to add particle tracers to this suspension. So now here on the screen, you see the protein solution loaded with polystyrene tracers. And so let's load this sample into the sample chamber. And I will now show you how to acquire a measurement on the NanoLab software. So here you can now see the main window of our NanoLab software. It was developed with the best tools and techniques available for Windows and with the idea of making it extremely user-friendly. The basic idea is that we start with a set of tiles and that each tile corresponds to a task. For example, we can perform DLS particle sizing, DLS microviscometry, we can browse through experiments, we can create and run protocols, also known as SOPs, and we can also import data that had been previously exported. So let me show you now how to perform a microviscometry experiment. First, I'm naming the experiment and keeping it simple here. I can set the sample name. It's not mandatory, but it's good practice. So here we are working with BSA at a concentration of 10 milligrams per milliliter. I need to set the tracer particle radius, and here we're working with polystyrene spheres with a radius of 53.5. I need to set the solvent, and I can choose among our preset solvents, or if my solvent is not readily available, I can choose custom and input the refractive index manually. I can also change the temperature anywhere between 4 degrees and 85 degrees. In this example, we are keeping at 20 degrees. And I can also set the measurement parameters. So either of the correlation geometries available here, autocorrelation, 3D cross-correlation, or modulated 3D cross-correlation. I can set a given number of repetitions per measurement. And here, to keep it simple, to keep it short, we'll stay at 1 repetition of 1 minute. I can name the measurement, and I'll here just simply name it BSA with the right concentration. At last, we also need to set the laser intensity. I can do so by setting a target scattered intensity, in which case we automatically have the software adjusting the laser intensity to yield a scattered intensity of 200 kilohertz. I can also set the laser intensity manually, and this comes handy in the example of protein solution microviscometry, because as Peter mentioned earlier, we need to assess that the scattering signal of the tracers overshadows the scattering signal of the protein solution. So here I'm going to set a given set point here and start the detectors. And let's see which value we have here. We are between 200 and 300 kilohertz. This is a good value to proceed. So I'll stop the detectors now, and I will replace the sample I have in a NanoLab by the pure protein solution. So let me insert it, and then turn the detectors on again to verify the scattering signal intensity. So here we have less than 1 kilohertz. So this is more than 100 times less than the scattering signal of the BSA plus tracer system. So we are safe to proceed with the measurement. The scattering, the intensity correlation function that we measure with the BSA plus tracer system will not have any contribution from the protein themselves. So I'll stop this measurement here, and I'll replace the sample again in the sample chamber. And we can now proceed with a measurement. So here the laser intensity is set and the photodetectors are switched on and the measurement is starting. In the next window, we see the correlation function with the cumulant fit, which yields the viscosity value, and also the value of the intercept, which is the crossing of the correlation function with the vertical axis. It's important to know this value because it shows how much signal is lost to multiple light scattering. If we were to measure a dilute suspension of particles in modulated 3D cross-correlation, we would see a value of 0.7 to 0.8 for this intercept. So here we have more than half of the signal that is lost to multiple light scattering, and the correlation function that you see is contains only contributions from single scattering events. That means that the results of the viscosity that we have are accurate. They are not compromised by multiple light scattering. And also we can see after some time, after about a minute of measurement here, that the value for the viscosity is more precise. Okay, so we are back at our main measurement window. We can view the measurement that was just recorded here. Here's the correlation function with the intercepts and the resulting viscosity. I could add one measurement to this experiment by simply clicking here and then entering the parameters that I may want to change. For example, increasing the temperature, changing the type of sample, or adding repetitions. And here I would simply click on Start the measurements. But for now, we're interested in looking at the results. So let's go back to the main window of the software and click Browse Experiments. Here's again our demo experiments. But here I'm interested in viewing some experiment that we pre-recorded for this webinar. So here you can see the structure of our experiment. It is composed of measurements, which are then composed of several repetitions. Within the repetitions, you can see the correlation function and again the concrete trace and every parameter that constitutes the measurement conditions. You can view all repetitions together. So here I'm looking at the viscosities that were recorded and the mean resulting value, which is here 1.52 millipascal seconds. I'm interested here in showing you the difference with these measurements to another measurement which was recorded in autocorrelation mode. So in this case, there's no removal of multiple light scattering. And then we see again the viscosity value, and the mean this time is at 1.63 millipascal seconds. This is more than 5% higher than the results in modulated 3D cross-correlation, for which there is suppression of multiple light scattering. So with this example, I really want to emphasize the importance of using an instrument which is capable of suppressing multiple light scattering. One can also view the measurements side by side, and here you can see that you can view the viscosities, their mean value and their standard deviation together in the same graph. And within this set of measurements, you can also add more measurements. So here, if I were to click there, we could also start a new DLS viscometry measurement, and you could also perform a DLS particle sizing measurement. And so that's it for the demonstration of this LSLab software. So let's go back now to the main presentation. So in this presentation, we've seen the principle of microviscometry, the challenges and the solutions associated with the technique, and how we have implemented it in the NanoLab 3D. As Peter mentioned earlier, you can not only do microviscometry with the NanoLab, but also particle sizing and other measurements such as static light scattering, which allows you to determine the molecular weight of your sample. So you get several solutions in one compact and easy to use instrument. You can also store and reuse the sample in our sealed glass cuvettes, which allows you to perform shelf life studies on your protein solutions. And if needed, you can use a sample volume as low as 4 microliters. You can also, and importantly, perform measurements that are fast and artifact-free. This reliability is important in this case because in microviscometry, we need to add particle tracers, as explained earlier, and we do so in a non-negligible quantity. And we could then be facing inaccuracies in our measurement due to the high concentrations involved. And so with the suppression of multiple light scattering with the modulated 3D technology, this is a problem that we do not face with this instrument. And I would like to wrap it up by mentioning a few references, which you can see here on the left. I would also like to encourage you to visit our website for more information. You can also subscribe to our newsletter, which we publish at a frequency of once per month. And you can also follow us on social media, either on LinkedIn or on Twitter. And I invite you to stay with us for a live question and answer session, which we will start in a few seconds with Peter. So I would like to really thank you for your attention. And at this point, I would like to hand it over to Peter for the first question of the Q&A session.